Welcome to the lecture of the material science. So today we are going to talk about X-ray. But before we talk about the X-ray, let's have a quick record about what we have learned in the last lecture. Last lecture, I think we learned single crystal, and then single crystal can be made naturally or artificially. And we also know that there are some applications for single crystals. For example, the blend of the turbine, or for the diamond for the abrasive application. The second one is polycrystalline material. As you can see here, and we have the polycrystalline is kind of combination of small single crystal, and then they make it together. So you can see that there are some small crystal, and we call it gram. And there are two types of the gram. One type is called equal axis. Equal axis means that in any direction is equal in terms of the shape or direction or structures. The second type is called cardinal. Cardinal is that, as you can see, that this is the gram looks long. So the property of this direction and this direction will be different. So this is the gram, and between gram and gram there is a boundary we call gram boundary. So there are four characters there are four characters of this in this gram boundary. Can anybody tell me what are these four characters? Pick up one, 0.5 point, early bird. There are four types of, I should say, there are four characters of the gram boundary. Anybody want to tell me? Yes, please. Okay, thank you. High mobility, thank you, 0.5. Another three chance. Raise your hand. High diffusivity, thank you. Thank you. Another two? Yes, please. High chemical reactivity, right? Okay, the last one, last choice. Anybody want to raise your hand? 0.5 points. Your final score, yes, please. Low density, thank you. So there are four characters of the gram boundaries compared to the gram itself or compared to the single crystal. And these four characteristics are very important when you do some of the calculation or you do some of the experiment. These are very important characters. I want you to remember this. Okay? Right, so this important thing here. And then the polycrystalline material, how do we make polycrystalline material? There are only two steps. Okay? That's what we call solidification. You can start from the molten metals and to become solid metal. Only two steps. The first step is what? Nuclei. You need to firstly make nuclei, right? And the second one is called growth or formation. Okay? So you have small nuclei and become bigger and bigger. From this small in the center and become bigger and bigger, it become gram. So this is what we call solidification. Okay, and the third topic is anisotropic and isotropic. Anisotropic, we divide this topic into two parts. First of all, we think of the single crystal in terms of the anisotropic or isotropic. And we all understand anisotropic is that crystallographic directions. It depends on the crystallographic directions and also the crystal structures. So the crystallographic direction means what? You have elongate a gram, or we call cardinal gram, and the property of the materials in this direction and also in this direction will be different. That's what we call crystallographic direction. So the property will be different in terms of what? In terms of mechanical property, in terms of electrical property, in terms of mechanical property, optical property, chemical property, or thermal properties, right? Okay, so this is called crystallographic direction, like 111 direction and then 110 direction. The property will be different. The second one is called crystal structures. As I just told you, the 111, 100, 110. And this also depends on the cubic and the cubic structure or triclinic structure or hexagonal structure. Okay. So for the polycrystalline, it's always mostly is isotropic, unless you have cardinal or equal axis grams. Okay. So this is the topic we talk on Wednesday. And we already talked about X-ray a little bit on Wednesday, and I just want to skip this. So let's have a quick recall. The X-ray, the wavelength of X-ray is between 0.001 nanometer to 10 nanometer. Normally, we regard the wavelength of the X-ray is about what? 1 angstrom, which is 0.1 nanometer. Okay? And the energy of the X-ray, you need to follow Planck-Einstein relations to get the energy. So if you regard X-ray, wavelength of the X-ray is about 1 angstrom, the energy will be 12,400 electron volt, which is very high. Okay, compared if you think of the ionization energy for elements, you know the number compared to this one is very low. So that means that X-ray has a very heavy or very strong energy to kick out the electrons in the atom. That's why we found out that this is the reason we can generate X-ray. We have an example of the X-ray use. We have an example of the gas discharge tube using hydrogen. So if you have very less elements, a very low pressure, which is almost vacuum, and you have a very strong voltage, and you hit the anode. Anode assume is a metal. For example, copper is a metal. So you can generate X-ray. So we already talked about this X-ray and discovery of X-ray, and we understand the X-ray transition can be regarded to like this. If the X-ray generate from the K shell, from L shell, M shell, or N shell, we use this we call the energy is K, wavelength is K, right? And if the electron cascade from n equal to 3, 4, 5, 6 to the n equal to 2, the wavelength of this is called L and M. So we have K alpha, K beta, K gamma, K delta, K alpha, K beta, K gamma, something like this. So this is how we understand the X-ray transitions. And if we recall what we have learned in chapter 2 about hydrogen spectrons, we understand we can use Ribert equation to represent the energy of this transition, right? Okay, how about the X-ray transition? We can use Ribert. We can use this Moseley law, right? Moseley law is a kind of empirical law, which is a modification of the Ribert equation. Okay, so you can simply calculate, but it is the answer you can get is not exactly the right answer. The answer you can get is the number is close to the correct answer. So this is what we call empirical law, right? So this is also, we understand this is called mostly step later, right? Okay, so this is also this kind of cascade is kind of characteristic X-ray. What does that mean, characteristic X-ray? It means that if you have a copper in your gas discharge tube, and if you have a moly in your gas discharge tube, or you have tungsten in your gas discharge tube, the X-ray you can generate will be different. And the information we can get from the X-ray is the characteristic X-ray for copper. This is for copper, this is for moly, and this is for tungsten. And if we think of a specific X-ray, for example, K alpha 1 for copper, that will be 1.5 angstrom. The K alpha 1 for the moly, that will be 0.709. If the K alpha 1 for tungsten will be 0.209 angstrom. So this is, so once you have an unknown metal and you put it into the gas discharge tube, and the X-ray come out, the wavelength of X-ray come out is 1.5 angstrom, and you can realize the unknown metal is copper. Okay, so this is what we call characteristic X-ray. So it depends on the, this is the energy and this is the elements, or we can say this atomic number, right? You can get this kind of series. So please read characteristic X-ray, information about the characteristic X-ray here by yourself. Right, so because we understand the element can be identified by X-ray. So nowadays there are many modern technology can find out the elements you use or the element you want to observe. So the characteristic X-ray are emitted when outer shell electrons feel a vacancy in the inner shells of an atom, releasing X-rays in a pattern that is characteristic to each element. Okay. So why inner shell of the atom? Why? Because I told you that the X-ray has a very high energy, right? So characteristic X-ray can be used to identify the particular elements from which they are emitted. So this property is used in various techniques, including X-ray fluorescence spectroscopy. We use XRF for short, or particle-induced X-ray emission, energy dispersive X-ray spectroscopy. We use XEDX, or the wavelength dispersive X-ray spectroscopy, WDS. So these are all called element analysis. So this is the machine or instrument you want to use. For example, this is XRF. You put an unknown metal in, and you can get a spectrum. And spectrum, if you use the spectrum, if you use a database to see, to put the X spectrum into the database, you can realize what kind of elements you want to know, you are observing or you are analyzing. So identification of unknown spectrums and the chemical analysis. So not only you can identify unknown species, but also you can have a chemical analysis. For example, if you have a compounds, or you have alloy, for example, like aluminum nitride, or you have some kind of silicon carbide, you can identify these kind of compounds. So this is one of the example showing you that if you have an unknown alloy, you don't know what is the elements inside, and you put this alloy into this machine, and the spectrum come out like this. And you can and if you check the database of this peak, and you will realize, oh, this peak with this energy will be the iron K alpha, or this one will be barium K L beta 1, something like this. Okay, and then as a result, you can understand this is an alloy, which is a combination of the many elements. like silicon, aluminum, iron, calcium, or barium. So this is a very useful tool for you to know the unknown elements, metals, or alloys. So here I want to show you an X-ray spectrum with a metal called rhodium. So this is when you have an unknown metal, or if you have a rhodium metal and you put into the X-ray discharge tube, the spectrum come out like this. This is the wavelength. This is the intensity of the peak. So the spectrum of the X-ray emitted by an X-ray tube with a rhodium target operated at the 60 kilovolt. Okay, and the result come out like this. You might wonder, Professor, in last lecture or just now, we only understand you can find out the characteristic peak or the characteristic X-ray. Well, what happened to this one? There's a curve which is broad, it's not sharp. What's going on with this? So this is what we call characteristic X-ray peak. And especially in this range, the wavelength is in a few less than 100 picometer. And this is what we understand, and also what we called characteristic X-ray peaks. Especially this is the K line here. And we also understand this is the characteristic X-ray the X-ray is quantized, because what? Because this X-ray is generated by an electron which cascades from outer shell to the inner shell. So the energy is quantized. Okay, energy is quantized. However, we want to understand there's a continuous curve here. The continuous curve is due to sorry, it's a German word, Bragströmham, the Bragströmham, and the spikes are characteristic K lines in rhodium. So the curve goes to 0 at the 21 picometer. Is in agreement with the Duhem-Hunt law, as described in the text. Okay, so there are three informations in this X-ray spectrum. The first information is characteristic X-ray. The first information. The second information is continuous curve, or we call continuous X-ray, or you can call it Bragströmham X-ray. And the third information is this. You need to follow the Hunt's law, the Duhem-Hunt law, to get this almost reach to 0. So and we already introduced you the first information, and let's talk about the Bragströmham X-ray, and also the Duhem-Hunt law, which is the curve goes to the 0. Right. However, if you use this is the information tell you that if you have a material A and material B, and the curve here using the same voltage in the gas discharge tube, and you will get different shape of the peaks, shape of the X-ray. So this can represent A materials. The K line is here, and B material K line is here. Okay, so this is different. So typical X-ray spectrum show you that you have different X-ray curves using different materials. Okay. So let's think of how Bragströmham X-ray generated. So the Bragg-Strongham produced by a high energy electrons deflected in a electrical field of a atomic nucleus. So as you understand, we know that if we have instant electrons, and the instant electron hit this atom, and the electron change the direction, that means what? That means energy has been exchanged, or energy has been gained by this atom. And because we know the conservation of energy in a system, so this energy needs to be released from this atom. So, and then the form of the for this releasing this energy is in the form of the light or electromagnetic radiation. And in this case, the Bragg-Strongham, who is the scientist, found this phenomena, and that's why we use his name to address this X-ray, and we call this Bragg-Strongham X-rays. So you can have an elastical scatter electrons, or you can have elastical scatter electrons. No matter what, if there's involved any energy exchange, you can generate Bragg-Strongham X-ray. So this is Bragg-Strongham X-ray. Okay, and this one show you that if you have energy one, if you have an electron here with the velocity v1 and energy v1, and this electron or this particle pass through this element or these atoms and change the direction, and leave this atom, and in the end, this electron the energy of this electron become E2, and the velocity of this electron become V2. So if you have the E1 divided by E2, E1 minus E2 will be equal to the energy of this photon. So that's why high energy and then instant electron with a high energy, and this is scatter electron with low energy. As a result, it comes out with X-ray. So the energy of X-ray will be equal to E1 minus E2. Okay, easy, right? However, if this instant electron change a little bit direction and velocity, this E will be different. So as you know that this energy is not quantized, it's continuous. Okay, it's not quantized. So Bragg-Strongham has a continuous spectrum which becomes more intense, and whose peaks intensity shift toward high frequency as a change of the energy of the deaccelerated, the speed decrease, right? The accelerated particle increase. So as you know, you will get a curve like this. So if the wavelength decrease, that means energy increase. The energy increase, and you find more particles. That means that intensity increased. The intensity of the photon increased. So you get this shape we call well-shaped curve. Well-shaped curve. So the X-ray is the combination of the Bragg-Strongham X-ray and also the characteristic X-ray. So low angle scattering and this high angle scattering. Okay. So now let's already introduce two important points of the X-ray, and third important point is called Duane-Hunt's law. So Duane-Hunt's law, named after American physics William Duane and Franklin Hunt, gives the maximum frequency of the X-ray that can be emitted by Bragg-Strongham in an X-ray tube by accelerating electrons through an excitation voltage V into a metal target. So this energy completely convert to the photon energy. Okay, so energy of instant electron become the energy of the photons. So energy of the electron become the energy of the photons. That's why the intensity, the wavelengths go to the minimum and the intensity go to 0. Okay, and that's why the shortest wavelength we call lambda SWL will be equal to what? This is lambda SWL will equal to what? This is the energy, right? This is the energy. What is this equation called? Planck-Einstein equation or Planck-Einstein relations. Okay, so this is the energy you want to know. And EV is the energy of the instant electron. And EV is the energy of the electron. You can realize that if it is equal to the charge of the electron times what? Voltage. So you can easily find, because this is input, so you can calculate, you can realize these two numbers easily. So you can easily to calculate lambda here by tuning your voltage in the gas discharge tube. Okay. So there are some information about Bragg-Strongham. Please read this by yourself, and I think I already explained this all to you. So now let's combine these 3 points together. Characteristic X-ray, Bragg-Strongham X-ray, and the Duan-Hang's law. We got the minimum, minimum wavelength. So X-ray comprise characteristic X-ray peaks superimposed on a continuous Bragg-Strongham X-ray. So you have continuous X-ray and a characteristic X-ray, which is peak and is blow peak. And this is, you put these two, combine these two together, you will become, it will look like this. Of course, if you have a small peaks in your characteristic X-ray, you will see nothing in the combination of the X-ray spectrum. Okay, unless the intensity of the peak is higher than the continuous curve. Okay, so the electrons from the cathode coated with anodes materials, usually tungsten, moly, or copper. Okay, these 3 are the most common metals we use in the X-ray tube. Okay, and accelerated other electrons, ions, and nuclei with the anode materials. Actually, there are only 1% of the energy generated is emitted and radiated. Only 1%. So you can only get 1% of this. Usually, the perpendicular to the path of the electron spins as X-ray. So the rest of the energy is released as a heat. So you have a efficient, you have the you have a energy from photon, you have energy from the heat. So this is an example to showing you that X-ray from a moly target at 35 kilovolt. You got K alpha, K beta line here, and this is Bragg-Strongham continuum or Bragg-Strongham X-ray. Okay, and you got the shortest wavelength. You can calculate this by Duan-Hang's law. Okay, so it depends on different voltage. That means that depends on different energy of the electron beam or voltage in a gas discharge tube. If you have a small voltage, you got nothing of the characteristic X-ray. So in order to get characteristic X-ray, the voltage need to be larger than the threshold voltage, so that you can get characteristic X-ray here. For example, if you use 5 kilovolt, you got nothing. 10, 15, 20, you got nothing. You cannot get characteristic X-ray, and unless the voltage, which is 25 kilovolt, which is greater than the threshold voltage. So you can get these two characteristic radiation. Okay, so you have to increase the voltage again in order to find out the characteristic X-ray. Right, so this is how modern X-ray looks like. So you have a target, as you can see. This is target. It looks like copper, right? Copper, and this is the generator of the electron beam. So between these two, you use a very high voltage of using this high voltage, and then this is called heated filaments. This is a filament emitted electrons by thermal ionic emission. So this is what we call hot cathode. Hot cathode. It's very hot. So you generate very high energy electrons. And because you generate very high energy electrons, and electron got minus charge. So if you have a cathode here, electron will strike. Electron beam will, or electrons will go to this anode very fast with a very fast speed. Okay, and because of very fast speed, electron has a very high kinetic energy, and there will be a energy matter interaction, right? So you generate X-ray. You generate X-ray, and you need a window to let X-ray to come out. Normally, as you can see, is here. Is here. Other place you just cover with the lead. You just cover with lead. So first criteria you need is vacuum. There's no air, or there's no molecules, or no atoms, no gas in this gas discharge tube. Why? Because if you have gas inside, the electron will hit gas before electron reach to the target. So you reduce the efficiency, you reduce the energy, which you don't want it to be happen, right? So no growth. So no growth, no collisions with gas. So you have more efficient. And this is what we call hard cathode. Hard cathode generate plasma, and plasma has electrons. So rise temperature to reduce the binding energy of the electrons in the cathode element. Sorry, this is cathode and this is anode. I'm sorry. So the cathode material here. So I don't know whether you have heard about hot cathode or cold cathode. No, when you use cold cathode, we call it field emission. But anyway, this is too far from you to know. Anyway, this is what we call hot cathode. Now they have cold cathode to generate X-ray. Okay. So because this is very hot, you use high voltage, it's very hot. So you need to have a cooling system here, and also cooling system here, because it will generate, all the electrons will hit this anode, and you will become very, very hot. And so the cooling anode in this place, so you can continue to operate. You don't want this tube overheated, right? So next is, you don't want X-ray to come out with any direction. You just want X-ray to come out only one direction. So other direction, other place you need to cover. So first of all, you have a lead shielding. You know, lead is a very heavy, and you have a lot of electrons in the lead atoms. So you have many energy levels because you have many atoms. You have many electrons. So X-ray can absorb on these electrons and re-emit it. And once X-ray re-emitted, that means what? It's not X-ray anymore. It can be it can be visible light inside, or it can be heat, right? IR, infrared, or it can be a very less energy. So which is not harmful for human being. Okay, so you need to have a lid to block the place where you don't want X-ray to come out. And then, of course, you need a window. which is barium. Barium here. Barium, why? Because barium has a low atomic number, which is only 4 electrons. So it's very difficult for X-ray to have interaction with barium, right? Okay, so very few energy levels. So it's easy to come out without with less absorption and the re-emission. Okay, you got more high efficiency of the X-ray. You might ask, wow, Professor, barium is number 4, so why don't you choose number 3? Yeah, why don't you choose elements which has 3 electrons or which has 2 electrons? I'm sorry that lithium is unstable in the air, so lithium will have very high reactivity with oxygen. So you don't have a lithium window. Okay, but can you use helium window? Can you? No, you cannot use helium window in this temperature, right? But if you reduce the temperature down to like 0.1 Kelvin, you can make helium window, right? You can make helium window. At that time, the helium is a gas. Lithium. Helium will be a solid helium. But anyway, it's very difficult. I hope you still remember we talked about this. Why helium can become solid? By what? By what? Why helium gas will come together? What kind of energy or what kind of attraction between helium atom and helium atom in order that they become helium solid? Or let's say the ice, what's that? Dry ice, carbon dioxide. What kind of force make carbon dioxide molecule get together, becomes solid? What kind of force? Anybody want to tell me? You still remember? There are 4. Anybody still remember? What? No? Raise your hand. 1 point in your final exam. Yes, please. Thank you. Excellent. London's dispersion force, right? Okay, London's dispersion force. Very good. I give you a lot of points today. Okay, I hope you are happy with this. Okay, right. But anyway, we cannot operate this X-discharge tube in the 0.1 Kelvin, right? No, there's no way to do this. It's not practical at all. So anyway, so barium is the best choice for us to use in the modern X-ray tube. Right. Röntgen is a great person. Why? After he find out X-ray, there are many applications nowadays you use. For example, this is the picture he took with his wife's ring here, and this is the bone of the fingers of his wife, the bone of the finger of his wife's human body, and this is the balance. This is the box, and you use X-ray, you can find something inside. If you have a cup, this is a case. This is the case of this box, and it's made of wood. So if you close it, you see nothing inside. Okay, but if you use X-ray, you can see this, and also you can see this is also Röntgen's. The picture from Röntgen is also a picture from Röntgen. He said that, well, I have a rifle, and there's metal in the rifle. I don't know this rifle is good or not, or there's any defects or any broken metal inside. I cannot see, but if you use X-ray, you can see. So there. Thanks for this. Thanks for Röntgen, his invention or his discovery. You can use this for your for your body and see any tumors in your body or what. Or every time if you go overseas, you need to have a airport security check, right? You need to put all your stuff in pass through this X-ray, so the security will know that whether you have a gun or very dangerous weapon or dangerous tools in your box or not. I remember there's one time my little girl put a scissors into my box, and I just passed through. I don't know, because she used scissors to have fun, to do some small cutting. But anyway, the security stopped me, say that I have a thesis which is not allowed to take into the airport. Anyway, so it's very good, this kind of X-ray. So in order to thank him, anyway, he got the first Nobel Prize in physics, the first one, Nobel Prize. Okay, and now his lab is a museum. Nobody can touch. This is a museum, and it was his lab. Now it become a museum. Okay, and this is a kind of things that this is kind of this paint, a very famous paint, oil painting made by a French very famous painter. Okay, and he sell, this is priceless. Now it's priceless, very, very expensive. And then when this paint just released, there's a guy who, he is Dali. He said, well, he said that the story of this paint is talking about it. They say this, there are many potatoes in this basket, many potatoes. So these two farmers, they thanks the God to give them the potatoes, so they can have, they are very happy. They are very happy. So the basket of potatoes. So Dali said, no, this is not potato. When I first see this picture, it's not potato. It's a dead baby. It's a dead baby, infant. Okay, so this scene is not a happy scene. It's a kind of funeral scene. Funeral scene means that these two people, or this couple, probably husband and wife, they are praying, say that, oh, my little baby, the dead infant, my little baby died. We feel sorry. This is the dead baby. And why it become a potato? A basket of potato. If you have a dead baby here and they are praying, this is a kind of sad story. You cannot sell. You cannot sell a good price, right? Okay. So in the end, they think that, wow, this Miller, this artist, he changed from dead infant to become a basket of potato. They don't believe him. They don't believe Dali. So they use X-ray to find out, is anything changed, be repented or not, using X-ray. And finally they find out, yes, it is. This is he changed. Okay, so this is the use of the X-ray, a kind of story. In Taiwan, also you can find this. Now, if you go to Tainan, you can see these 4 characters in a temple. But it was not like this. 8 years before, it looks like this. Okay, and then they change these 4 characters to become this. Okay, so they use X-ray to find out this. Right, so this is the summary. Okay, this is for the information for you from the K line, L line, M line, N line. This is the information for you to know. Right. So next topic will be X-ray diffraction. We call XRD, X-ray diffraction. There are 2 types of X-ray diffraction. The first one is called Lowy diffraction, which is the transmission diffraction. The second one is Bragg law, which is reflect diffraction. So next topic will be X-ray diffraction. There are 2 subtopics, as I just told you, Lowy diffraction and the Bragg laws. So now we start from Lowy diffraction. First of all, again, what's diffraction? You have if you have slits and in the water, and then you make the water flow, vibrate, and you can get this kind of disturbing pattern. So diffraction is the phenomena inhibit the wave fronts that passing the edge of a opaque body. Opaque, that's what we call opaque body, right? Modulated, thereby causing a redistribution of energy. This is energy. That's why it moves within the front. Okay, no problem. So the X-ray diffraction is, you know the diffraction. Everything can make, if the particle has the behavior of wave, always diffraction. So what happened to X-ray? X-ray also has a diffraction phenomena. So what's X-ray? So when a beam of X-ray imprints on a solid material, this is solid material. You have atoms which is packed together, and we have distance between atoms, right? That's what we call what? If this plane and this plane, what we call d-spacing, right? Interplanar spacing. Remember, this is what we call in this plane and this plane we call interplanar spacing. How do you calculate the space? By equation, right? I hope you remember that's the Kahoot on Wednesday. Right. So a portion of this beam will be scattered. So you have a distance here. You can regard this distance as a kind of slit. Okay. So if the wavelength of this electron magnetic radiation or this photon is close to the distance between two atoms, that means what? You can have deflection, right? So by the electrons associated with each atoms or ions that lies within the beam path. So this is called diffraction grating must have the space. It has to be spacings comparable to the wavelength of the diffraction radiation. So this radiation or this photon has a wave. The wavelength need to be very close to this distance, so you can find out the diffraction. Okay, cannot resolve if the spacing is smaller than lambda, right? If this is too small, I'm sorry, you cannot find. Or if this is too big, this X-ray doesn't work for the diffraction phenomena. So spacing is the distance between the parallel plane of atoms. So that's what we call this called spacing, interplanar spacing, right? Okay, so let's take a look of the Laue diffractions. Laue diffraction, easy. If you have a crystal, and of course this crystal need to be single. The X-ray pass through this, and you have a collimation, collimator to make the X-ray beam collimates, okay, very straight, and then pass through this crystal, and you get pattern here, because this will have X-ray diffraction, and you can find some of the pattern like this. So this is the spots generated by electron beam. So electron beam will pass through this directly and have a very strong pattern, have a very strong spot in the center. However, you can find some small spots surrounding this spot in the center. And this spot created by deflected X-rays. Okay, so by identifying the direction and the distance of these small spots, you can identify what kind of material is this, or which plant is this facing to this X-ray. That's things you can find out. So crystal, because it's a regular three-dimensional lattice, as I just told you, right? You have single crystal which is packed very well and packed very well in order. Okay, so we regard this as a kind of deflection grating. So you can have deflection pattern, and this X-ray is very strong, so you can pass through this as Laue diffraction pattern. You can find this is what we call Laue diffraction pattern. So spot patterns is imitative of the symmetry of the atom arrangement. So this is called Laue spot. This is in order. You can see that, well, this is not randomly distributed. The spots are not randomly distributed. This has a kind of symmetry. For example, if you cut here, you will find out that this looks like a mirror pattern. So what I want to tell you is that this pattern not only tell you what kind of material you are looking at, but also can tell you what kind of planes facing to the X-ray. So this is what we call rotational symmetries. We call folds. For example, the plane 100. What's the plane 100? This is the plane 100, right? 100. 0 means infinite. 0 means infinite. So this is the plane. So this, if we look at this plane and the X-ray directly hit this plane, we'll find some of the patterns. How can we identify what plane we look at? There's an easy way which we call fold. For example, this is 100 plane. And if you rotate this plane, and then you will realize once you rotate to 90 degree, you will return to the original shape. You will return to the original shape. So the important thing is you pick up the rotation center first, and you start to rotate, and you see what degree you rotate, and then you will reach to the original shape. And fold is the equation of this. Fold is 360 degree divided by base angle of rotation. So this is base angle of rotation. So you rotate 90 degree. So this answer will be what? This answer will be 4 folds. 360 divided by 90. Because once you rotate 90 degree, it becomes original shape. And this is what we call 4 folds. So you can rotate this. You can rotate this. And we'll see if you rotate 90 degree, that means you are looking at the 100 plane. How about 110? 110 is this one. 110, right? 110. 0 means infinite. So you are looking at this plane. So this is not a cube. This is not a square. The length of x-axis and length of y-axis is different, right? So, and then let's take a look of rotational symmetry. So how many degrees you rotate in order to reach the original shape? It's 90 degree, 180. So how many folds in this case? There are 2 folds. 360 divided by 180. So there are 2 folds. So if you have a mirror pattern, that means you rotate 180 degrees and you match the original shape. That means you are looking at 110 planes. Ladies and gentlemen, here I just talk about very simple case, which is cubic structure. Okay, only cubic structure. There are more complicated structures here. Okay, how about 111? 111 here, right? 111. So you have a center, rotational center. So how many folds here? Please tell me. How many folds? Easy, right? So if you turn 100, because you know 160, 360. So you divide it into 3. That will be what? 120. 120. 120 is 360 divided by 120. That will be 3 folds. So, but according to this kind of simple calculation, you understand which face or which plane facing to the X-ray. So if I give you a picture like this, could you please tell me how many folds? Just rotate, right? Okay. And you will find out this is 360, just 1 fold. You cannot find out crystal structure like 1 fold. No. Okay? And how about 5 folds? If you change, and this is 5 fold. Unfortunately, among that 14 crystal structures, there is no 5 folds. Anyway, just for your information here. Right, so this is the Lowy pattern. These 3 are the case for you to understand this. The Lowy diffraction pattern here. So this is 4 folds. If you have a pattern like this, it will start to turn 3 folds. Okay, this is 11100 plane, and this is 3 folds, which is 111 plane. This is 4 folds, 2 folds, which is 110 plane. Okay, but at this moment, you still don't know what is this material. You just know this is 100 plane. You don't know this is a metal. This metal is a gold, silver, or platinum. You don't know. But you need to, in order to find out this, you need to do the calculation of the distance between these points. Okay, Laue diffraction is used to measure the crystal orientation. The numbers and the arrangement of these spots depends on the type of the crystal. Okay, so the number and the arrangement of these spots depends on the type of the crystal. It can be metal, it can be gold, it can be silver. Okay, it can be copper. And on its orientation is related to the beam. The beam means what? X-ray beams. Okay, you might ask, Professor, can I use electron beam? Yes, you can. That's another story we are going to talk next week. So Laue pattern contain information of the symmetry of a crystal. However, it is impossible without any additional data to establish unequivocally to which of the 32 crystal groups of a crystal belongs. Okay, so these are some of the ready example of Laue pattern. This is the pattern of silicon with a Pyronosus 110. Okay. Okay, this is polycrystalline, zinc chromium. Okay, what's the superimposed? As you can see, there are some single crystal. If you see the spots, this is what we call single crystal. If you see the ring, that means what? Polycrystal. Why? Because the ring tell you what? The ring tell you that you have small grams of a single crystal and you pack its kind of particles. You have thousands and thousands of particles put together. So it's randomly distributed. Because the orientation, the random distributed, and then so orientation won't be uniform. So as a result, when you use this and use X-ray to pass through these 100 particles, you got many different directions of scattering. As a result, you got a ring here. So this is what we call is polycrystal. However, if you have amorphous material like glass, if you have amorphous glass like glass or SiO2, amorphous material, they pack not in order. So when you pass through X-ray, what can you get here? You got nothing. There's no spots. There's no rings. Only a blue bright image. That's it. Okay. So according to this kind of pattern, you can simply identify single crystal, polycrystal, or amorphous. Okay. So this is a powder samples. As I just told you, if you have many particles here, it's not single crystal. So when the X-ray pass through this, this can be 111, it can be 100, it can be 001, for example. So the direction you can get is a kind of ring here, not a spot, not spots. So this is what we call the Debye-Scherrer pattern. Okay, a sample of hundreds of the crystal can be powder sample. You have powder. They put powder, you have thousands of the particles. And it shows that the diffraction beams form continuous cones. Okay, a circle of the film is used to record the diffraction patterns as shown here. Okay, and each cone intersects the films given a diffraction lines. You have diffraction line here. These lines are seen as an arc in the films. Arc, right? Arc. Okay. Lowy get Nobel Prize because of this. So in 1910, it was not certain whether X-ray or wave. Okay, but Lowy suggests that if the crystals are periodic with the interatomic distance of about 1 angstrom, they might act as a diffraction grating toward the X-ray waves. So you use copper sulfide. They use copper sulfide to identify Lowy's idea. So Lowy has an idea, and these two gentlemen, scientists, demonstrate copper sulfide as a material, and then they X-ray pass through this material and get patterns. So they get a Nobel Prize. Very good, right? Okay, so this is the first story of the X-ray diffraction, which is Lowy diffraction. And second one is called diffractometer, which we call it Bloch's law, or the X-ray is not passing through to get pattern, but instead of passing through, they use diffraction, refraction, and diffraction pattern together. So assume if you have a very bulk and very deep, very huge material, and you cannot let X-ray to pass through and get a pattern completely, and X-ray might refract, right? So this is called interference. There are two types of interference. One is called constructive interference. The second one is destructive interference. The first constructive interference is first of all, you need to have a very good beams which has the same length, wavelength, and same amplitude. Okay, and these two waves has a kind of scattering event. Scattering event means what? You might have a slit, right? You might have a slit. You might have a gap between two balls, and then the X-ray passes through. And after interaction, these two waves present the same behavior. And as a result, and this is what we call constructive. After constructive, as you can see, this wave has the same wavelength but different amplitude. That means what? That intensity will be doubled. Intensity will be increased, right? This is what we call constructive interference. How about destructive interference? Destructive interference means what? Again, you had two parallel beams which have the same wavelength and same amplitude. That's what we call coherence, right? Another one is they pass through the same speed, same pattern. And after you go through the scatter event, unfortunately, these two destructive. Okay, these two reduce their intensity by one to another. And then as a result, you got nothing. There's no wave come out. And this is what we call destructive interference. I'm sure you have learned this in your high school. But what we want to know here is that, let's think of this, not using water, but using X-ray, very small wavelengths and very small space between atoms in a crystal. So diffraction of X-ray by a plane of atom, it looks like this. And this is very important because we use this as a kind of fundamental knowledge to generate X-ray diffraction pattern. So assume you have an instant beams, two instant beams, and this is the a material, which is unknown material. And this is the atoms in the material. Of course, you know that this is the D spacing or interplanar spacing, and we understand we use DHKL to represent the spacing. Anybody want to tell me the equation? How do you know the equation? You know, right? Okay, so first of all, the X-ray There's three important information you need to know. It's better to be laser, okay? Because this X-ray has a coherent interface radiation, okay, coherent. And it should be monochromatic, a single lambda. The lambda need to be same. And it need to be parallel. So coherent means that if you get together, if you raise your hand on right hand side, raise your right hand, he need to be raise his right hand. Anyway, okay. So this is first one, and second one is that instant beams, right? Parallel and lambda. Okay, and you have A, B, and D spacing here. So, and you have an angle, instant angle, theta here. So X-ray will shoot to this material with this angle. And this spacing tell you that this is the equation. I'm sure you understand. And then interesting is that interference, constructed interference tell you what? Tell you that the scatter X-ray 1 and 2, that's if this is constructed interference, that means what? The wave, the beam come out will be, the intensity will be double. That means we can see, right? If the destructive, we see nothing, so we cannot record. So the difference of the path length, you know, if this is the constructive interference, the only difference is the length of these two paths is this one plus this one, right? If you have parallel beam here, and the difference between the distance of this, the differences of the path for these two beams will be only s distance of sq to the qt, right? Sq to the qt. And what? And you know, in order to have constructive interference, this need to be integer times wavelength. Integer means what? It can be 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, right? So n lambda equal to this one, sq, the distance between S point and Q point, plus the distance between Q point and T point. And how are you going to find out the distance of the SQ? By D, right? This is theta. This is theta. This is instant angle. So this is theta, right? So sine theta of this D will be the distance of the SQ, right? And also the sine theta of the D will be the distance of the QT. So ladies and gentlemen, I want you to remember this equation. This is very important. So n lambda equal to 2D sine theta. Okay? This is important, and I might need you to do calculation in your final score, in your final exam. I should say the celebration of learning, right? Exam is too heavy. Exam too heavy, right? Celebration of learning. That's a very nice word to use. Do you agree? No, you don't. Very heavy, right? Exam is always very heavy. But I give you a lot of points during the lectures. I'm sure you can pass without any problem. Right, so this is called Bloch's law. What's the Bloch's law? M lambda equal to 2D sine theta. N is integer, can be 1, 2, 3, 4. And in order to obtain D, in order to obtain the interplanar spacing, if you know, because lambda is X-ray, right? So you know the lambda. N is integer, of course, you can put 1, 2, 3, 4 into. Okay, so theta is the instant angle. So you can decide. You can decide the instant angle, right? So the only thing unknown is what? D spacing. So in order to know the D spacing, you need to know the lambda, N, and the sine theta. Okay, for the case of the cubic crystal structure, you need to know the D to A. Okay, this is A, and this is D can be here, right? Or it can be A. So it depends, right? If the cubic structure, the A equal to B equal to C, things will run out of our time. Okay, this is spacing. So, and you can put this D in here, so you can find out A. So, first step, find out D spacing. The second step, find out what? A. So you will know the edge length, right? You can find out edge length. For example, I just give you an example. I give you this, and you find out the D spacing of the plane 110, and you can get a edge length. No problem. Okay. So this is also the fingerprint of the crystal. I think we run out of time today. Although I want to talk to you more, I think let's leave this the rest of the materials to the next week. Okay. Right. So I hope you enjoyed the lecture today.